let me recall what we have been doing. Okay. So we have a CP map from MN C2. We have been discussing characterizing CP maps between MN and MM, some other matrix, some other two algebras. Okay. We proved that, we proved the following is linear, is a linear map. Okay. Then the following are equivalent. We proved the following. One, P is CP, completely positive. Completely positive means one tensor phi. If you just take one tensor phi from MKC, MK tensor MM to MK tensor MM. Okay. This will be positive for all K. Okay. Where positive means it takes positive elements to positive elements. P is CP is equivalent to saying P is N positive. There we can take the K to be N itself, where this N is this N. P is N positive. It is enough if it is N positive. And 3, if Pn equal to Eij tensor Eij, where these are matrix units, it's 1 in the ijth place. These are Eij in Mn. See, which are matrix units. Then you take the summation over I and j. Okay. All these matrix units, Eij tensor Eij. And this is something, this is in MNC, this is in MNC, so this is in Mn tensor Mn, MNC tensor MNC. Okay. Then it is enough if P of Pn, which we call it as P phi or something. This P is misleading. We will think that P is projection. It's not a projection. It need not be a projection. P phi, this is greater than or equal to 0. It's enough if it is greater than or equal to 0. All these things imply that there exists V1 up to V D. D is what we use. Okay, last time, it's better, we want to look at the reference. So I said that it's mapped from CM to Cn, but let us take it from I'm just shifting the star to this. Okay, that's all. These are mapped from Cn to Cm. I took it from Cm to Cn, but let it be from Cm to Cn, such that P of x equal to summation Vi x Vi star. I equal to 1 to D. This is Vi. Sorry, V1 up to Vd. Correct. That's okay. These are all maps. All these things are D maps from Cn to Cm, such that these are. So we proved this. There was some confusion, which I would better. The confusion, the proof, there was a confusion with respect to this N and M. I said something which was wrong. There is some confusion I made, but the proof is correct. What we do is the following. Of course, this implies this is clear. This implies this is also clear. And this to this we have already proved. 4 implies 1 we have already proved. Only 3 implies 4 we have to worry. So 3 implies 4 is a P phi, which is a positive matrix. So it's supposed to look like this. Small VL. It is supposed to look like this, where some J is what I used. J or okay, IER. Maybe I've used J. Okay. J equal to 1 to B. Okay. Then suppose this Vj, this Vj is like this, yeah. Vj, where this Vj is in Cn tensor Cn. If you have any positive matrix that is going to be in this form, follows from spectral theorem. Okay, and the P phi is in Cn tensor Cn. This is a matrix acting on Cn tensor Cn. So this vectors will be in Cn tensor Cn. P phi is in Cn tensor Cm. Pn is in tensor Cm. This is Pn is in Cn tensor Cn. So this is P phi of Pn. This P phi is going to be Cn tensor Cm. Okay. So which are vectors, n vectors containing Cm. So Vj is going to look like, Vj is a column vector. So it is going to look like some W1 up to Wm. It's going to look like this. Okay. The thing is, this is a NM vector. You can write it as a n cross m matrix. Then you define your, this is small vj, corresponding to this, you write capital Vj. You want this Vi, you want to define this Vi or something. Okay. This is from Cn to Cn, so it should be a m cross n matrix. M cross n matrix. So this is n cross n, so this should be m cross n matrix. So m cross n matrix means you should have m row. So you have m row here. So you just B1 up to, sorry, this is n. So this is n, sorry. This is n. This is this omega I. This is in Cm, sorry. This is in Cm. Okay. So you just write it. So this is a column vector. So this is just, you just write it like this, omega 1 up to, you just, I mean, this is a column vector, m cross, this is, of course, this is a column vector. So you are just writing it as omega n. So this is the m cross n matrix. Okay. This is a column, m cross n. So if you have small Vj's like that, then you get the capital Vj's like this. This is the corresponding. So, I mean, everything else is fine. You just write it and just, you have to just verify the multiplication. I would like you to verify that. Okay. Okay. So I also would like to verify the following. I mean, that there is this. So then we proved the following. So we also proved that. We proved this using this. I mean, using this association. We proved that P phi is greater than or equal to 0, imply that phi of x looks like this. Then it is completely positive. So we also proved the Choi rank of phi is exactly equal to rank of phi. P phi is a positive matrix, and the rank of this is exactly, Choi rank is the minimum number of, you can write it in many ways. The minimum number of D is what is the Choi rank of this, and that is exactly equal to this. That also we proved. Okay. So this is just this fact you should, this fact you should keep in mind. So given any completely positive map, we always have a matrix operator or matrix, P phi matrix, an operator between Cn to Cm. We always have this. And the connection is the following. If P phi equal to summation that Vj, okay, then you can always this Vj corresponding to this V, then this is always the case. It's the other way also it is true. If, other way one way is, of course, that is how we construct. The other way is, suppose if P phi, if P phi is given by those small Vj's, vector small Vj's, then this capital Vj's can be defined like that. Conversely, if you have any capital Vj such that P looks like this, then the corresponding P phi, which is defined by this, is exactly given by those Vs. This is the correspondence between that. If P phi, suppose if it looks like this, Vj, okay, j equal to 1 to D, okay, then corresponding Vj, the capital Vj, or basically you have to write this. How do you write? This Vj contains, you have to write, Vj is a very long vector, you have to write it as a matrix. Okay, where this Vj. No, I want to say the other way. Sorry. If Vj looks like this, then P phi looks like that. You understand what I'm saying? It is just the correspondence is 1, 1. Okay? This is the bijective correspondence between that. Okay? So then it is this way. Okay? Conversely, let me write it. Conversely, if P of x equal to summation Vj x Vj star, okay, where j equal to 1 to D, then the P phi, which is defined like that, is given by summation small Vj, where this Vj comes from this Vj. Okay? You have a matrix, you just write it as a n vector. Okay, where Vj is given. I mean, I don't want to write. It's clear, right? So that is the correspondence. Okay. The reason I want to remember this correspondence is the following. We want to prove the following. Is because of this. So we want to prove the following theorem or proposition. It's usually called as Stein-Springs. It follows from Stein-Springs theorem. We can prove this for general C-star algebra using GNS representation. Here also we can use GNS representation, but I don't want to do that. Okay, we want to use matrix theory, linear algebra to prove this. Okay. So the proposition is the following. So let P from Mn C to MMC is a CP map, is CP, okay, and P of x equal to summation and CP and the P equal to R. Okay, the Choi rank of P is equal to R. Okay, suppose that means there exists Vj. Suppose P of x equal to summation j equal to 1 to R V j x Vj star. Okay, and P of x is also equal to summation L equal to 1 to some D, okay, where Wj x Wj star. You have two representations. Suppose if you have two representations, one representation is given by the Choi rank, where R is equal to that, and the second representation is given by D matrices, Wj's, okay, where again all this Vj, Wj, they are all matrices. They are all matrices from Mn, I mean n cross n, m cross n, n cross m, yeah, Cn to m cross n. Okay, they are maps from Cn to Cn. Okay, they are all this V1 up to Vr, W1 up to Wd. They are all in m cross n. Okay, yeah, m cross n. So you get a vector. Okay, m cross n. Okay. Then there exists a matrix U from, it is a matrix from CR to CD. Okay, there is a R, there is a D. Okay, that is U is a matrix and D cross R matrix, such that is U is in M, D cross R, C, which is an isometry, that is U star U equal to 1 R, and summation U J L D L, okay, L equal to 1 to R equal to WG. Okay. These are all matrices. Of course, it is like, I mean, if you just consider scalar, it is just the U acting on that vector gives this vector, but instead they are all matrices. You can write it as tensor and something. We'll come to that. I mean, it's actually a notation in tensor, but I spelled it out like this. Okay, it is like this. So this is the condition. This is an isometry. Okay, this is U star U equal to 1 R. Okay. Of course, it will not be. If it is D is equal to R, it will be a unitary. Okay, so this is, we want to prove this. Okay, this is part of this may be called a Stein spring or something else may be called. Let us call this a Stein spring. Okay, Stein spring, STINES spring, SPRING, Stein spring. Okay. This is a more general theorem for general completely positive map. It gives it's a representation theorem, Stein spring representation. It gives. We will come to that using partial trace. We will define that also. We'll get that. Okay. Okay. So this is what we want to prove. Okay. So proof. First, we prove enough to prove the following. Enough to prove the following. Because we have this correspondence, we have this correspondence between V and VL, small v and capital V. We have this correspondence. If that did I write that? Yeah. If Vx is given by this, then Pφ is given by this. Okay. So if Px and if these V's are intertwined by those, this is some sort of intertwining, intertwined by this U, then it is enough to prove that this V's and there will be corresponding WL. Okay, so that will be intertwined by that. Okay, so it's enough to prove the following: if P phi equal to summation VL VL Vj, J is what is J, J equal to 1 to R is also equal to L, this is L equal to 1 to D, WL, WL. Okay. Suppose we have two representation of this P phi, it is enough to prove the following. Then there exists a U, the same U in M, B cross R, C, okay, such that U star U equal to 1 and the same thing, summation L equal to 1. I have intertwined J and L. I mean, I want to use J for this and L for that. This is okay, it's not a confusion. Now, I have just, I mean, here it has to be J and L are, I want to use J for this and L for this. Here I have changed to something, I mean, that's okay, okay. So, summation J equal to 1 to R, okay, U of Lj, Vj is equal to WL. Okay, these are vectors. Okay. To prove that for matrices is enough to prove that. It's the same thing. Okay, just get convinced. It's clear, right? If we prove, I mean, these are all vectors, which for this it is true, then it is true for that also. Okay. Okay. So this is what we want to prove. Okay. Okay. So we will prove using several lemmas. So our aim is to prove this. Okay. If you have any single matrix, so if you have some positive matrix, so it's enough to prove the following. It's enough to prove that suppose if we have any positive matrix, okay, we can forget about n, d, where m and l are all those things. You have some positive matrix which is written like this, and it's also written like this. Then there exists a unitary. I mean, here R is here, D is here, okay, and this positive matrix in some n, that is enough. Okay, in some n cross n matrix, that's fine. So then there exists a unitary between them such that this satisfies. And then there is an isometry such that it satisfies. So that's what we want. So I take, so to prove, so let A be greater than 0, any matrix, I call it A for now. Okay. A looks like this, summation J equal to 1 to R, and rank of A. You know the Choi rank of phi same as the rank of P phi. So it's enough to consider the rank of A equal to R. Okay. A such that Choi rank of, I mean, this is just the usual matrix rank of A is R, summation such that A looks like this, VL, VL, okay, VJ, VJ, okay, VJ. And this is also equal to L equal to 1 to D, WL, WL. Okay. Then we want to get a unitary between them. So suppose we assume that we want to get that unit, I mean, isometry between them. Okay. So suppose if this is true, then the first claim is, then this is lemma 1. Okay. Lemma 1. Then the range of A equal to span is finite dimension. We don't need to take closure and all. V1. Actually, we don't need this. Another thing, I'm sorry. I mean, the lemma is just this. I mean, we have two things. So there will be then range of A is equal to span of just this DL, Vj. 1 to R. Sorry to Sorry to change. I'm sorry. I'm extremely sorry. I mean, actually, I want to use the, I want to prove that, but as a lemma, this is the lemma. Okay. The lemma is just this. The lemma is you have a positive matrix. Now we are not considering rank. Okay. And A is equal to summation Vj, Vj. Just that's all. Okay. J equal to 1 to some D. Okay. Whatever. Then just this. Okay. Then the range of A equal to span of Vj. Vj. Okay. 1, 2. Okay. Then we will come to that. Okay. This is what you want to prove. I mean, it will imply that we have two representations, and span of those WL is also same, span of those Vj is also same. That's what we want to consider, and we want to prove that. Before that, we want to prove this lemma. Okay, is that clear? Is it clear? Okay. How is it clear? Eh? Yeah, it is. Proof is just clear. You take any, I mean, you want to prove, so range is just A something for, I mean, the range of A. You take any A, that is just going to be summation j equal to 1 to d. It is just going to be Vj, right? Vj. I mean, this is a scalar times Vj. Of course, this is in span of that, okay? Span of V1 up to Vd. But you have to prove the other way. Other way is clear? Why is it clear? Take inner product with what? You have to prove that. Other way is you have to prove, we only need to prove this. This Vj is in that range of K, right? Each one of them is in the range of K. How do you do that? Huh? Vj by norm of Vj. If you take, you have to get a xi, I mean, no, Vj is in the range of A. So you have to get a xi such that A xi equal to this. You can choose Vi, you can choose Vi. Yeah, that will give that, right? Does that give? Huh? No, they're not working with this. They are just something. They need not, they are not even assumed to be linearly independent. They are not even linearly independent. Okay? So I think we have to go through spectral theorem. Okay? It's not direct. I don't think it's not direct, right? So suppose, so I want to, so suppose let A equal to, so suppose I mean, by spectral theorem, okay, A will look like this, summation lambda I, some ei, okay, lambda I ei times u star, okay, I equal to 1 to whatever, r or whatever. Okay, that is how it will look like. A looks like some, where u is unitary. I mean, sorry, let's call it V, something V is a unitary. Okay, V unitary by spectral theorem. Okay. Then notice Vi, any Vi as an operator. This is of course greater than 0. This is a projection greater than or equal to 0. This is less than A. I mean, some operator is less than A if that minus this is positive. That's the definition of that. This minus this is just the linear combination of other rank 1 projection. So that is greater than or equal to 0. So this is greater than or equal to 0. Okay. So this is greater than or equal to 0. So this implies, notice that you take the same Vi, this V star. This is nothing but UVI. I mean UVI, okay, and UVI, right? UVI, okay? UVI. This is clear. Not UV. Okay? if you apply, if you get, I mean, it will just verify this. Okay? It's basically this. So if you have some A less than or equal to B, then for any unitary U, UA U star is less than or equal to UB U star. Just you can take, I mean, B minus A is greater than 0. If you take this, I mean, you will get U of B minus A U star greater than 0. And if for anything positive, I mean, if anything positive, UD U star is anything D positive, this is greater than or equal to 0. Okay? Actually, you have to verify each and everything. Okay? So if A is less than or equal to B, then this is equal to, I mean, this is just U of B minus A U star. This is positive. Okay, if you have anything of this form is greater than or equal to 0, because you can write it as A power half, and I mean it's of the form some D star D. So because of that, okay. So because of this UVI, VVI, V capital VVI, this is less than or equal to UA U star. Okay. And UA U star looks like something like this. I mean, this is just some matrix lambda 1 up to lambda D or whatever. Okay. 0, 0, 0. Right? That's how it looks like. Okay. So, but then this should also look like something here. Then this implies that VVI should also looks like something star 0, 0, 0. I mean, if you have something less than that, it cannot have anything here. Okay, you please verify that. That will mean that that will contradict the possibility. First, you can prove for this is 0. Then you can prove, I mean, if it is positive, this has to be the star, and I mean, you can use all that and you can prove this. Okay? You can sit and prove this. Okay? So this implies VVI equal to summation some mu I times that EI. I mean, it is just a matrix here. This is the rank 1 projection. This is a vector. So this vector is linear combination of those eigenvectors. Eigenvectors of A. Okay, VVA looks like this. So now this, I mean, this is a vector. Okay, now VI is equal to summation mu I. Here actually this lambda is greater than 0. Okay, where did I write? Yeah, this is lambda is greater than 0. They're only strictly greater than 0 we are taking. I mean, those eigenvalues we are taking. Okay? So mu I by lambda I. Okay, right. Summation A of summation mu I. This is equal to V. This is okay. Sorry, this is equal to U A U star of this. That is that the diagonal is. U A U star acts as lambda I on this EI. So that lambda I will cancel. You will get only mu I. Summation mu I is this. Okay, because of this, it looks like this. Okay. So this implies Vi equal to U star of this. So if you take U star of this, A of U star of whatever we have, something. So A of something. Okay. So this implies Vi is in the range of. I don't know whether this can be simplified than this. Okay. So what we have proved is if A is a linear combination of this kind of one-dimensional projection, then A is the span of those vectors. Range of A is the span of those vectors. That's what we have. J equal to 1 to R, yeah. 1 to D, okay. I will get confused with these things, okay. What I mean is if it is written in this form, then the range of A is a linear span of this vector. That's what I want, okay. Okay. Now let us come to the proof. Okay, okay, we want to use this. So what we have is the following. We want to prove this. P phi looks like this and P phi also looks like this. So P phi is a linear span of this, P phi is a linear span of this. Okay. Okay. So I will continue this proof. Okay. So suppose P phi is looks like this, and P phi also looks like this. Okay. Maybe you better finish writing. Yeah. If it is not clear, you ask me. Okay. Yeah. It is just from the spectral theorem, and it just follows. Okay, so suppose P phi looks like this. It's a linear span of this one-dimensional projection, rank one projection, and it is also a linear span of these things. Okay, and here rank of P phi equal to R. Okay, this is rank. Rank of P phi is equal to R, okay, which is same as the Choi rank of that. Okay, we are assuming. Okay, then first range of P phi equal to span of those Vj. J equal to 1 to R, and which is also same as span of WL, L equal to 1 to D. Okay. Now, this is, these are R vectors, and the rank of this is, the rank of P phi is R, means this has dimension R. So this is a basis. Okay. So in particular, Vj's are linearly independent. J equal to 1 to R is linearly independent. So they are linearly independent. Okay. So there exists, WL can be written like this. There exists U, L, J, okay, such that WL is equal to summation. It's a linear combination of all those V's. Okay, summation U, L, J, Vj. J equal to 1 to R, because they are linearly independent. Okay. Of course, WLs will not be linearly independent. They may be, they just span. Okay. We can write it like this. All we have to show that this is unitary. This is an isometry. That's what you have to show. Okay, we only need to show this. Okay. Okay. So we have the following. We have P phi looks like this and also looks like this. We want to use that. We haven't used it. Okay. So we have summation VL, Vj, okay, J equal to 1 to R is equal to summation L equal to 1 to D, WL, okay, and WL can be written like this up to R. So I use I and I prime here because I have to sum it. So summation L equal to 1 to D, okay, summation, let me just write it, okay, I prime. You will write the WL, you write it like this and take the ULJ. These are scalars, you take it out. Okay, and here take it out as bar. Okay, so we will get summation over I and I prime U. So U Li, here you have Li, and U Li prime bar, okay, Vi prime. Okay, it's right. Vi prime. Okay, here I have written I prime. Okay, is clear? You will get a summation here of this VU using that. You will get a summation here. I have just taken the scalars out. That's all. Okay, and there is a triple summation. There is a two summation here, and there is one summation. There is a triple summation. Okay, now I just take the L inside and interchange the summation. Okay, you just interchange the summation. I erase it. Okay, maybe I erase it. This is okay, no? I can erase it because this is what I want to prove. I erase it. Okay. So this is equal to summation over I prime. Okay. And if you just sum it over L, okay, this is just the ILth entry of U star. U star, I mean, is Li, so it transpose me ILth entry of U star. This is the Lith entry of U. Okay, so I just bring it here. Okay, so this is the summation U star U. Okay, LLth entry, right? Now it will become I prime entry. This is summation over I. I mean, I just take the summation here. It's okay. Should I write it? I take the summation over L here. Summation over L will be U of I prime entry. Okay, of this matrix U star U. Okay, that is clear. Okay, of this Vi prime. Okay, this is fine. I prime. Here I prime here. I prime I, correct. Doesn't matter. I prime I. You are right. Yeah. This is I prime I, Vi prime. Okay. We just have, we just want to conclude about this. Doesn't matter how it comes. Okay. Now this is equal to, we have something here. Something here. This is a linear combination of these kind of things. Okay. We have, so if we prove the following lemma, prove this Vi prime, these are all matrices. Okay, rank 1 projection, these are all matrices, are linearly independent. Okay. In I and I prime. This is a n square element of linearly independent. Okay. So if we prove these are linearly independent, then you have a linear combination, this linear combination of all these things, then that will imply that U of I prime, I prime I or whatever is equal to delta I prime, delta I prime I. Here we have only one element, Vj, J equal to this. That's what we have. Here you have the linear combination of all those things. Okay. So all those lambdas corresponding to, I mean, it should match, exactly match, because they are linearly independent. Okay. So the ith element, if I equal to I prime, then they are equal. So that should be 1. Otherwise it is 0. So all we have to prove is this is linearly independent. So this is the lemma we have to prove. Enough to prove this lemma. That this lemma is, if V1 up to V, whatever, V R, okay, are linearly independent. Okay. Linearly independent. Then this Vi prime, okay, where I equal to 1 to R and I prime equal to 1 to R, this is linearly independent. Is that clear? I don't think it's very directly clear. We have to prove it. If V1 up to Vn are linearly independent elements, then you take the rank 1 matrices given by arbitrary, taking each one of them, Vi prime. So those matrices, rank 1 projection, that is also linearly independent. Okay, that's what we want to prove. Okay. No. There are R vectors. This is, yeah, there is no R cross R. There are totally R square elements here. These are all some vectors, some n element. I mean, we are supposed to consider m and n or something. We forgot about that. We don't care about it. They are proving a general lemma. We have some vectors in something. This is all something in some Cn. Some Cn, CD, Cm, whatever. Okay. Then this is a n cross n matrices. There are R elements here. There are R square elements here. If these R vectors are linearly independent, Then these R squares matrices, I mean, the number of elements here R square. Those matrices are linearly independent. That's what we want. Okay? So proof, we assume V1 up to Vr are linearly independent, then we want to take it. So suppose some summation, some lambda ij, Vi, Vj, okay, equals 0. We want to prove lambda ij's are 0, assuming that those vectors are linearly independent. From that we have to. Okay. Okay. Now we have this, of course, V1 up to Vr are linearly independent. Okay. These are some n vectors, n column vectors. Okay. So we just write it like this: V1 up to Vr. Okay. This is in M. This is n rows are there, n cross R. Okay. Right. This is a vector. This is a matrix here. We just write it like this. So this is injective. That is because linearly independence. Okay. So suppose the proof of this is, suppose to call it A equal to this. Okay. Yeah, I think that's what we'll do. Suppose A of something lambdas are there, so maybe alpha 1 up to alpha n equals 0. Okay. Then that is just this is just equal to summation alpha I Vi equals 0. This implies alpha I equals 0. So it's injective. Okay. Kernel is 0. Okay. Okay. Now we want to use this A, and suppose we have this. So this is a matrix. Okay. So let some xi is in Cn. Cn is a vector space we are working with. Okay. Then this is 0. Then summation lambda ij vi vj xi equals 0. That's what it means. That means it is equal to 0 means exactly that's what it means. Acting on any xi is 0. That is summation lambda ij. You take this vector vj xi acting on vi equals 0. Now each vi's are linearly independent. Okay, each vi's are linearly independent. This implies for all I, summation lambda ij, okay, vj xi equals 0. Okay. Okay. For all I is fixed. Okay. Now, if you take lambda to be this lambda ij matrix, okay, where this is R cross R matrix, right? It is R cross R. Lambda ij is R cross R. R cross R. Okay. Yeah. Okay. Then this is just this thing implies that lambda now we have that lambda is, yeah. So lambda acting on what is So we have lambda equal to lambda ij, lambda ij. All we have to prove is we want to prove each lambda ij is 0. So lambda as a matrix is 0. That's what we want to prove. So okay. Now lambda, this lambda acting on what we have A, let me just write it. A star xi equals 0. Okay. This is for all xi. Any xi, this is 0. So for any xi, I mean, this is what is A star xi? A is those vectors, right? A is this thing. A star will be just V1 up to Vr. A star is just V1. You take this vector, okay? The adjoint vector, Vr. Okay. Now xi is some xi1 up to xi(n). Okay. So it is precisely that. A star xi is that. Whatever. A star xi is just this. Okay. A star xi is that. So this is just this just says that lambda of A star xi is 0. Now A is injective. A star is onto. Okay. That's clear to you. A is injective, A star is onto. We will just write it. Okay. So all we have to prove, since A star is onto, so A star xi is all vectors. Okay. So this implies lambda is equal to 0 as a matrix. That implies lambda ij equal to 0 for all ij. Okay. Now we only have to prove, all we need to prove is if a matrix A is injective, then A star is onto. Okay. It's equivalent actually. That just follows from, kernel of A is equal to range A star perp in finite dimension. In infinite dimension, you have to take the closure and other things. Okay. That you can prove it. Leave it as an exercise. Yeah, it's clear. You just take a vector here, you just take the inner product. I mean, something is 0, if and only if its inner product with everything is 0, and using all that you can prove. Okay. So it's clear, no? So it fall. So proof follows as kernel of any A, anything is range of A star per orthogonal complement of that. Okay. Is equivalent to that. So if A is injective, means this is 0, this is trivial, singleton 0, and that will be everything. So from that you can prove. So that's all. So we have proved. We have proved the original thing, that if the completely positive map is given by two Choi-Kraus representation, then they are intertwined by an isometry. So that's what you have proved. Now I want to introduce something called partial isometry. Partial trace, not partial isometry, partial trace. Okay. So partial traces for tensors. Okay. So let X be in H tensor K. Okay. Usually in quantum system, we will have HA tensor HB. So here we are just taking one X in H tensor K. Okay. Okay. Of course, trace is just the sum of the diagonal thing, which you can define it using those. I mean, for any art, we have proved that trace does not depend on the orthonormal basis. Okay. So if we have H tensor K, then you define linear functional P from H to C by P of any X is equal to, you take X tensor, you want to take, I mean, you want to, yeah, I want to take that case out here, right? Yeah. So X tensor 1, you take X tensor 1, okay? You can, X tensor 1, you can take it. Sorry. X is there already. So you have fixed a X. This is for Y. Okay. For Y in M. This is supposed to be operator, sorry. Okay. Suppose L of H tensor K. I mean, well, the X is operator. Okay, X is an operator in L tensor. It's just if it is Mn, this is just Mn tensor Mk or something. Okay, it is an operator. Okay. So you define a linear functional from H to C such that phi of y, you take y tensor 1, then you multiply with X, then you take the trace. Okay. Trace on the bigger one, H tensor. Okay. For define phi from H to Y, again, L of H to C. Not H to C, L of H to C. I'm sorry. You have a X, you fix a X in L of H tensor K, then you define a linear functional free from L of H to C by P of any Y, okay, Y in L of H. Okay. You take equal to, you take Y tensor 1, okay, then you multiply with X, then you take the trace. Okay. This gives a linear functional, of course. Right? This gives a linear. If you have a lambda here, it will go lambda and you can take it as, and it's a linear function. Okay? This is linear. So now trace is an inner product. So by Rees lemma, I mean, this is a Hilbert space with respect to the trace inner product. Okay, so there exists X. There exists. I mean, you call it as trace B of X. You call that as trace B of X. This is the operator you are calling. If you want, you call it as Z or something. Okay, maybe okay. Maybe I will call it. There exists a Z in L of H such that trace. I mean, whatever that P of Y equal to trace of Zx, right? Z Y. Is okay because it's inner product. Because it's a Hilbert space and trace gives an inner product. I mean, because any linear function is given by inner product. Okay. So this is what is called partial trace. Okay, that is, I mean, call this Y, call Y as denote Y as trace. You are tracing with B of X. Okay. What we have, let me write it again. X is in L of H tensor K. Okay. Then this trace, not B, trace K. I mean, I wrote the B because usually in quantum system you will call it as XA, XB. So that's why I wrote B. Sorry. This is trace of K. Okay. So it is just the trace with respect to the second one. Okay. X is trace of X tensor, trace of Y tensor 1 X is equal to trace of, you call it as trace K X Y. This is okay, what I have written. This is for all Y in L of H. Huh? No, I call that Z to be this. Denote, sorry, Z to be. Sorry. Yeah. So this Z is called as a partial trace. This is what is called partial trace. Okay. So this is just a definition. We don't use any orthonormal basis and we don't use any representation. Just operator theory to define. So it is just well defined with respect to anything. Okay, but we don't want to, this is just to give the, abstract definition. Okay, abstract definition. But usually it is precisely this. So, I mean, if you have L of H tensor K, This is just matrices, right? If H is, maybe I call it a Cn. So if you have X is in Mn, C, and R, MMC. Then this partial trace is basically, I mean, so maybe we'll go treat it as quantum system. So if we have HA to be Cn, okay, and HB to be Cm. Okay. So suppose X is in M n cross M, sorry, Mn tensor MMC. Okay. Then the partial trace with respect to this Hilbert space, is just one tensor, the trace of another thing. You just take the trace. So suppose X will look like Xij, okay, where this is a n cross n matrix. So this is n cross n. With each Xij is in MMC, right? That is how X will look like. Then the partial trace with respect to that, whatever the HB of this X is nothing but this. You just take that. This is the usual trace of Xij. Trace of Xij. Okay? That's all. So this will become an n cross n matrix. This becomes scalar, so this becomes an n cross n matrix, and this is in MMC. Okay? So the partial trace is nothing but, of course, if we define like this, then that depends on the representation, orthonormal basis, with respect to fixed orthonormal basis. So we want to show that that is not the case. So that's why I defined it abstractly. You can verify that this satisfies that. I mean, this has to be verified actually. Okay, and I leave it as an exercise. Okay? You just have to verify this satisfies that property. Okay? The partial trace with respect to HB of any X is nothing but one tensor trace of this X. Okay? Trace will take to Mn to, I mean, this is on Mn, the trace on the second Hilbert space. So this will go to Mn to C, it's a linear functional. You have already given an exercise about this. If you have a one tensor phi, that gives a completely positive map. So the partial trace is a completely positive map. Partial trace is from Mn tensor Mn to Mn. Okay, I have already given an assignment for any phi. Trace is a linear function, so this is already. If you prove that, this is a CP map. Okay, CP.